and welcome back. And today we're working on this vacuum tube computer right here. This is the UE1, and it's a tube computer that we started building quite some time ago, but there was about a 6-month period in there where there was zero progress being made. We started by building the, what I've been calling UE14500, which was based very heavily on the Motorola MC14500, which is a little 1-bit industrial control unit that Motorola built to replace relay ladder logic in industrial situations. But it had a really interesting design, except for the fact that it only had a logic unit in it. So I did some modifications on this to give it a full arithmetic logic unit. But the way Motorola designed that chip, and well, the way that this is designed as well, is that it's not really a self-standing thing. It needs a lot of supporting circuitry around it to make it usable. So I was going to use this as a foundation and build out a full-fledged computer from there, and I let feature creep get the best of me, and it kind of ballooned beyond what was feasible. So in the previous episode, we took a moment to kind of redesign and think about where we were going from here. And instead of building out this huge monstrosity, instead, we're just gonna take another page out of Motorola's book, and we're gonna build the MC14500 Industrial Control Unit Display System, or the demonstration board. And I've actually already built one of these. That's what this guy is right here. This is pretty much following exactly the blueprint that Motorola laid out in their industrial control unit handbook. And I actually have a full video on this. So if you want to know how to build one of these yourself, you can check out the link in the description below to more on this guy. But this is the blueprint for what we're going to build next. So that's what we've been building. In the previous episode, we built essentially this portion down here with the 7 toggle switches and how that's going to input into the system. And today I want to continue building upon that and build out the rest of the logic that's necessary to get that input all the way up to the processor so it can do something with it. So let's hop over to the bench, take a look at where we are, take a look at where we're going, then we'll cut some PCBs up, solder them up, and give them a test. All right, we're trying to build the minimal ICU system out of vacuum tubes, and right off the bat, we're on the back foot here. The UE14500 is taking up essentially half of our set-aside real estate for this. I really want to keep it limited to just 2 of those backing boards, and one of those boards is full already with essentially the equivalent of this single chip over here, which means everything else on this board that's made out of ICs has to fit into a single one of those backing boards and be made out of vacuum tubes. That seems a little maybe not possible, but if we take a look at the ICU system itself, I think we can get there. At the bottom, we have 3 registers. We've got input, output, and scratch. And input is just going to be some switches. And that's actually what we started building last time with this piece right here. We've got our 7 toggle switches coming in. That matches our 7 system inputs right here. Looking at the rest of the system here, the scratch bits and the outputs, we actually have to build out of something. We need to make some kind of D flip-flops. And we already have a good design that was with our old way that we were building things. So we're gonna repurpose some of those boards and we're gonna make some new ones. The rest is all of this stuff up top. And this is just 2 4-bit counters and an EEPROM. And the EEPROM has an 8-bit address coming in and gives an 8-bit value out. 4 of those bits are used for the processor as an instruction. 4 of those bits are used for addressing. It's a really pretty clever design. And well, if we wanted to implement this like it was built on this actual IC version over here, it would be straight up impossible. But if we build it with paper tape, we can essentially eliminate all of that and just replace it with a paper tape. The minimal ICU system doesn't have the ability to jump, it just reads sequentially. So if we're just reading sequentially, tape is brilliant. So that's where we're going with this. But that's not where we're going to get to today. Like I said, we built this in a previous episode. This is the beginning of our system inputs, and I want to continue working on this today. So the system inputs down here needs a little more to get it going, and that's all outlined here. And this is a logic diagram of the entire system. Not quite the entire system. The paper tape is not included on this logic diagram because this was built in Logisim, and Logisim doesn't exactly have a support for a paper tape, not gracefully at least. So the paper tape inputs are just these 4 buttons that are in the top left here. Now the top half of this diagram is the UE14500, the processor that's already built. As you can see, we have the large bulk of this machine built already. Everything else is right here in the bottom. And this is actually interesting. It goes to show something really interesting about the IC version over here. Yes, there are a lot of ICs on this, but not all ICs are created equally. The MC14500 is much more dense and has far much more going on inside of it than all of the other ICs combined, with the exception of the EEPROM up here. So that is why I think we can stuff it all onto one board. Now, if we look at the bottom half here, it actually is just a bunch of D flip-flops. That's the large majority of logic. And that's just gonna be our output register and our scratch register. And we essentially have the scratch register already built. We just need to rip it off of the old board and repurpose it for what we wanna do. But we are gonna have to build the output register. However, today we're still working on system inputs. Now we have these 7 toggle switches going through inverters, and that's just this tiny little bit on the bottom. That's all we built in the previous episode. But in this episode, we're gonna build quite a lot more, and that is this entire bit here on the left. This is a kind of diode matrix or logic decoder that takes 3 bits of an address in and breaks it out into 8 individual logic lines. And it does that using essentially OR decoding based upon those 3 address bits and their inverse. And that'll give us 8 individual outputs that we can then use to address what bit we want to use in the scratch register, in the output register, or on the system inputs down low. Now that 4th address bit is used to switch between input output or the scratch register. Now, input output are actually 16 selectable bits there, but we only have essentially 3 address bits to select between them. So if we're writing, we use the write signal to tell it to write to system outputs. If we're reading, we have the write signal off, so it automatically switches over to these 7 toggle switches that are coming in. So that's how we're kind of achieving 24 bits of read and write access with just a 4-bit memory address. It's really kind of close to a 5-bit memory address, except that that write signal only kicks on when we're doing a store or a store complement operation. So we're just using that in a really smart way. So like I said, we're building this OR decoder here, and we're also going to build all of the NOR gates along the bottom here for the system inputs. Now these NOR gates again are working on kind of an inverse logic. We need to have all inputs into each 3-input NOR gate go low in order for the output of that to go high and to put a value onto the data bus. That's why we had to invert our toggle switches in the piece that we built in the previous episode. So for example, if that toggle switch is off, it goes into the inverter and the inverter makes that signal high, which then goes up into our NOR gate. And any single high signal into a NOR gate makes the output of that low. So we're not going to assert anything onto the bus ever. Now, if we flip that toggle switch on, the inverter changes that signal to low. So now we have a low signal coming into our NOR gate. Now the other 2 signals also have to be low. And one of those is our address select bit coming from our OR logic. And this entire selection thing works in inverse. Every single line is on except for the one that we currently have selected with the address. That particular address line is going to be low. So if we have a different address selected, that address select line that's going into our little NOR gate here on the bottom is going to be high. We have to get to the very specific address to get that line to go low. And if we are at that correct address, we now have 2 low logic lines coming into our NOR gate. But there's a 3rd input coming into this. And if we look, that 3rd input actually goes to all 8 of these NOR gates. And that is going to our 4th address bit. So that goes through a separate inverter that goes up to address bit number 4. And that inverse signal goes to the NOR gates on the bottom, our input, and the D flip-flops on the bottom half, our output. And then the write signal is going to be used in an interesting way to make sure that we're writing correctly. But we'll get into that when we get to building the output register. So, well, we now know what we have to build. It's just a collection of NOR gates, a couple of inverters, and a whole lot of OR gates over the top. So I'm gonna fire up the mill, cut out some PCBs, and then once they're done cutting, we'll solder them all completely up and give it a test. I'm actually going to cut up a total of 2 large PCBs and 3 smaller connecting PCBs. And you can see one of the smaller ones here closest to the camera. And everything seems to have cut really well, except for this first big board here. It had a low spot right in the middle of the PCB, which is like a really weird place to have a low spot. Usually it's off to a side or on an edge where I didn't get everything perfectly flat, but a low spot in the middle is a new one for me, but it was nothing that 10 minutes of work with an X-Acto knife couldn't fix, and that's actually pretty amazing to think about. To be able to cut 2 large PCBs, each being over 400 millimeters long, is pretty amazing. And with the PCBs cut, it's time to start soldering everything up, and there are a lot of solder connections to make on these, so it's definitely time consuming. But I just got the tunes rolling and jammed out while getting everything soldered up. And actually, someone in the previous episode on the Bendix G15 left a comment asking what's on my playlist. Well, my day job is Japanese to English technical translation, so I haven't really listened to music with lyrics for about 15 years now, because otherwise the lyrics end up in the translation, and that's never good. Of course, there's some exceptions, like the Fear Inoculum album from Tool, but for the past few weeks in particular, I've been on a pretty big Bonobo, Explosions in the Sky, and 65 Days of Static kick. All 3 are excellent bands with a ton of great albums, and well, Mick Gordon, Volta for Astronauts Satellites, Animals as Leaders, a lot of these have been getting playtime too. I mean, I could go on for hours about good music, but it looks like the soldering is just about done. And here is the finished product, and man, I think it really came out looking beautiful. But I did make 2 drafting mistakes, and they're actually both located on this single board over here. The first is a power mistake up here. I had all of this kind of scooted over a little too far, so I had to put a couple bodges on the bottom to get power flowing across the top. The second is that this end piece here doesn't have the connection for the data bus that comes out to go back onto the data bus. So we do all of this wonderful stuff and then we don't ever actually assert the data bus. So this piece on the end here is actually just junk. We'll go ahead and remove that. I'm gonna have to remake both of those pieces. But the rest of this should actually work, and it's fairly simple. Coming in on the left here, it looks like we have a phenomenal amount of tubes, but a large majority of this is just cathode follower buffers. We have our 4-bit address coming in. Each bit goes through a buffer and an inverter, and then the output of that inverter is buffered again. So each bit uses 3 tubes. So there's bit 0, bit 1, bit 2, and the final bit 3. And then we take those signals over to our wonderful diode matrix here. This is doing that address decoding that's breaking it out into 8 individual lines. So all of this over here is that part on our logic diagram that was kind of on the left that was taking our address and decoding it. And then over here on the right, we've got our collection of 3 input NOR gates, and you'll notice that there's 8 tubes, so there are 8 inputs coming into this. 7 are coming from our toggle switches, which is going to be this board right here. And then the 8th one is coming from the results register. So I think it's time to actually plug some power into this. I haven't powered this up at all yet. And let's see if we can put an address in here and get the appropriate output over here. All right, first test is a smoke test and power distribution test. I want to make sure that all of the filaments come up. There's a lot of tubes here that we're trying to power up at once, and if anything's going to pop, it's going to pop at this stage. So I don't have anything else attached. We're just testing the filaments. So we'll go ahead and flip the power on here. Those came on, that one came on. I'm seeing some filaments over here coming on. I have the lights off, so hopefully you guys on the camera can see this as well. But this is the toggle switch one that we built in the previous episode. I fully expected it to power up, no problem. It definitely looks like it is. This is the new boards back here. The 8 tubes on here all have glowing filaments, and the 12 tubes over here all look like they have glowing filaments too. So I didn't see anything go up in smoke. All the filaments came up. That's a good sign. Let's start plugging some inputs and outputs into this and see if we can't test some functionality on it. All right, I've got everything plugged in here and hooked up, and I think I'm narrowing in on a few issues. The first is that it doesn't seem like we're getting any output out ever. I've got the address set to multiple different addresses. Doesn't matter what I set that to. Doesn't matter what I set the input toggle switches here to. Just nothing ever comes out. So I stopped the camera and I pulled the multimeter out and I started doing some troubleshooting. And what we can see that, for example, on this one right here, we have 3 inputs going into our NOR gate. That one's at 1.4 volts, that one's at 2.3 volts, and that one's at 3.1 volts. All 3 of those are a low input, so the output coming out of it is at 4.9 volts. That's a low output. We should have like 20 volts coming out of that. That's really weird, and I tested that on a couple of different tubes here, and they all are like that. So I don't think it's a bad tube issue. And looking closer, there is a diode here installed backwards. This one on the very end is supposed to be facing the other direction. So that is definitely one problem. Okay, back together, and I think that did it. Right now we're at address 0000. So no matter what switch I flip, nothing's going to happen. We're never going to see an output on our little VFD over here because the 4th bit is set, and as long as that's set, we're actually working on the scratch register, not input over here. So we got to set that 4th bit on. So if we turn that on, we can see our little VFD comes on, and that's because the address is 000. And that is the result register loop around. And right now the result register is technically storing a 1. It doesn't exist, but the way this is wired up is that it thinks it's storing a 1. So that is now outputting to our little data bus over here. So that's actually working correctly. And if I change the address to 001 here, that kicks off. Now what that means is that we're now on this tube over here, and if I flip this switch down here, we should see the data bus come on, and yeah, check that out. So now if we go to 010, this switch doesn't do anything anymore, it's just always off, but the switch next to it, yeah, kicks our data bus on. That's excellent. So if we go to 011, and we go to the next switch, that works perfectly. So let's go to 100, we go to the next switch, that's working correctly too. 101, 110, and finally 111, and that is on. And if I take that 4th bit and I flip it off, it kicks off. This all seems to be working 100% perfectly. The only issue is that this VFD is pulling a bit more current than it should, and so it's not very bright, and that makes me a little nervous that the data bus output that's coming out of this probably needs to be buffered. So I'm gonna have to double check my design and make sure I've got a proper buffer in there somewhere, because if I don't, we might not get clean data bus outputs out of here. But other than that, this seems to be working absolutely perfectly. So there we have it. I think we made some pretty good progress today. We got quite a lot of the input taken care of, but we also got all of our address decoding taken care of as well, which means we can now use that to address and select certain bits of the scratch register and the output register. Now this is starting to get a little unwieldy here on the table, so I think the next step is to re-drill the wood for the new layout and start getting these boards mounted to the wood. This will let us start to see how it's starting to come together, and it'll let us test it a lot easier without having to have a million wires all over the place. I will have to make a bunch of new panels that allow me to connect these parts and the memory parts to each other, as well as, you know, remake this one that we messed up earlier. But we're really covering some ground pretty quick on this second half here. I'm really excited about that. I would say that with this and the 2 memory boards that we already have built from our previous design, that puts us about 30 to 40% done with the second half, or at least done up to the point of having to figure out how to design the paper tape. And that's how we're going to go about it. We're going to design all of the supporting circuitry and leave our paper tape input as just kind of a black box. And we're going to tackle that after we get all of the rest of the tubes built. So we still got a lot more work to do, but I am really happy with how this is shaping up now. So there's going to be much more consistent updates coming on this. So I hope you hang around to check out the future of this project and where it's going. And I want to thank you so much for watching today, and I hope to see you next time.